Good. Hello and welcome to Precalc C. Period 3. You missed class because of 3/4 of an inch of snow. It was great. So you will watch a video. Period 8, the real people in the room. Let's do a little bit of learning, then we're going to go over the homework, then we're going to do some more learning. Sound good? Woo! Alright, you may recall, like, we did this little activity called Intro to the Conics. And we did it midway through the unit, just before break. And it was the geometric definition of the conic. Let's slightly review that. Whoa. Carbon, can you pass out to everybody one of these pieces of paper? Sure. Good. So what is a conic, you may recall? Well, there is a line in this, stop talking, in this piece of paper coming around. This line is just called line A. And then we discussed what's the next thing that happens once you have a line. Remember, we're going to make a cone.
You tilt it.
Yeah. Yeah. First, maybe you want to pick a point, which is going to be your vertex. Let's call that point V. And then, you guys all said some things. Say them all again.
Make another line that's tilted.
You make another line that's tilted. Tilted by how much? An angle, which we call the vertex angle. Yeah. And so, so there's like, yeah, a vertex. So, this is my line A. This is my vertex V. This angle, which we call like alpha, is known as the vertex angle. So let's like this thing is called the axis of the cone, and this point V is called the vertex of the cone, I think is what they call it, and V is a point on A, and then this thing alpha is called the vertex angle of the cone, and then what comes next? And then we have these lines, as you guys were saying. And I don't know why I'm looking at this paper for guidance. I don't need this piece of paper. So we have so-called generating lines. So what is G? G is a generating line of the cone. If it intersects line A at point V and makes angle, or I'll just say at why am I having trouble with this? G is a generating line of the cone. If it intersects line A at point V, making angle alpha. Yeah. So cool. So this is a generating line. This is also a generating line. All of these are all alpha. And basically, we define the cone. So cone C is the set of all generating lines. Okay. And then using this sort of precise, we did all this, but we did it like just talking it out. We didn't like write it down. Cool? Okay. So then we make the conics. How do we make the conics? Yeah, a plane comes. Yeah. And this plane, I can't draw it very well, so I will first, yeah. Good. This plane comes, and what determines what kind of conic we get? The angle that the plane makes with the axis. So if this is my plane, and if someone wants to give me like art tips Who are my like artistic people in this room who can like just naturally draw very well? No one's answering, so you guys. Okay, good. So feel free to just be like, dude, Rose, that line needs to be dotted, like, or just jump up and like fix it for me or do something. All right. Anyway, we have a name for this angle. We call this angle theta. Okay, so just to make sure we all remember all this, please tell me, like, when do I get a circle, for example?
When you refer to the
Theta is 0. No, 90.
Yeah, can you give your answer in terms of theta?
Theta is 0. 90? 90.
Yeah, so if theta is 90, then we get a circle. Cool? Say cool. Okay, if on the other hand, well, when do we get an ellipse? Yes.
Theta is between 90 and alpha.
Yeah, initially you might be like, yo, if theta is less than 90, then I would think that we would get an ellipse. But as we have seen, that's kind of true. But if theta gets smaller and smaller and smaller and smaller, what happens when theta equals alpha? Everybody? What happens when the angle that the plane makes with the axis is the same as the angle that the generating line makes with the axis? That's when we get a parabola, right? Because this comes through and just goes... So a parabola is like an ellipse that never ends. Cool? Say cool. Okay, so since when theta... we're just summarizing all the things that we already learned, but we didn't have time to like... Well, we just didn't feel like writing this all down then, so we're writing it all down now. And so Ethan wants to say that really it's only an ellipse if theta is less than 90, but also bigger than alpha. Cool? Cool. Okay, and then what if the angle that the plane makes with the axis is even less than alpha? Then we get a hyperbola. Yeah? Okay. Alright, so if theta rather is less than, I guess, yeah, less than alpha, then we get a hyperbola. Okay. All of this is also assuming, if we call this plane like P or something, all of this is assuming that P does not go through the vertex. So this assumes that the is this all coming on the video, by the way? Yeah. You should like be over there and like monitoring. This all assumes that V is not on the plane. In other words, was it on? Yeah. Okay, good. In other words, that the plane was not going through the vertex. So these are like the normal conics. Then we also have the degenerate conics. And the degenerate conics happen when the plane passes through the vertex. So that the vertex is on the plane. So now let's go through each of these again. What if theta is 90, but the plane is going through the point? Point. Yeah, true. Now you have to violate the rules I said before and like.
Just keep moving it.
Yeah, or if you don't feel it's necessary, you don't have to. But
I got it.
I wasn't really doing anything important over there. If theta is 90, then what do we get? Point. What if theta is between alpha and 90? I think we should move when I go around. I'm about to do something cool. Yeah, you also get a point, right? That's like a point's like a degenerate ellipse. What happens if the angle theta equals the angle alpha, but also the plane goes through V? Then we get like a line, right? Yeah. Line. So if theta equals alpha, then we get a line. And this is the one that's hardest to see. If theta is less than alpha, but also the plane goes through the vertex, then what do I get? Like two intersecting lines. I get like a pair. I get like a pair of intersecting lines. Yeah. Pair of intersecting lines. Okay, cool. All right, that was all to just get us back in the game. And I mentioned at the time, and you either were like, but that you should have, or you might have, when you first heard this definition of ellipse, for example. So like our definition of ellipse is that basically this is an ellipse. But then what was one of our big problem was that we also had this other definition of ellipse, right? And I mentioned at the time that we must actually like resolve this. All right, so we're gonna do this right now. This is something that like almost no one does. This is like magnet program only, although really everyone should do this. It's not that hard. We are gonna prove that an ellipse is an ellipse.
Of course.
In other words, we are going to unify the definitions. I'm going to prove that this geometric object that you get when you pass a plane through a double cone at a precise angle is the same object that you get using the other way we defined ellipse, which is the locus of points to the sum of the distances to the foci is a constant. You guys with me? All right, and it's not obvious whatsoever that those should be the same thing at all. And it's not even clear how we would ever possibly do this. Well, we're going to do it. And we're going to do it via these things called Dandling Spheres. All right, I didn't actually prepare this lecture at all, but somewhere around here is a little cone. Oh man. Some years I put it back when I'm done. Some years I just leave it out forever. And also while I'm doing this, does anyone have like a small sphere, like a tangerine? Would, oh, you know what? I think I had a tangerine. Do you have a tangerine? Perfect. Okay. Also true, you might need to grab the camera and like go like handheld. All right, so here is like someone show him out. Like,
like take it off. Okay.
Does anyone know how? Yeah.
I know how.
All right, good. All right, so this is a cone. All right, this is a sphere. What happens if you drop a sphere into a cone?
It
Depends on the sizes.
Well, the cone's like infinitely large, so it goes down all the way to the bottom. No, of course it can't go all the way to the bottom. It will get stuck. And where is it gonna get? How? Like, talk to me about more about that stuckness. What kind of stuck or something? Is it going to get stuck on the like equator, so to speak, of the sphere?
No.
Equator?
Yeah, I'm asking you. Does it get stuck on the equator?
Yeah.
No, definitely not. No, it does not get stuck on the equator because like it's a cone, right? So it's like more down and like less up, right? So I want everyone to like get this. People at home, do you get this? Yeah, it's gonna get the sphere is gonna get stuck in the cone like somewhere in like the southern hemisphere of the sphere. Can I get Vigor's head nods if you get it? Okay, good. All right. In fact, now can I do this? This is okay, right? It's not gonna affect it. If you pour a little water in there, just a little bit, enough to get it all kind of wet. It doesn't seem to be working this particular time. Why is it not working? Oh yeah, there we go. This tangerine's a little weird. Well, it doesn't seem to be doing what I want it to do. But we're gonna have this. We are gonna have this so-called circle of tangency, and the circle of tangency is named after tangerines. The circle of tangency is the circle at which the sphere is touching the cone. Follow? And that circle of tangency is going to be a circle on the sphere, but like not the equator, like a smaller circle, a circle of some sort. And you can see it, the water is so that like you get kind of like this. You see how like you can sort of the circle kind of pops out, right? See what I'm talking about? You can kind of like see. People at home, you see that circle of tangency? Oh yeah. Okay. So that real world's happening. It's right here. All right. Good. Circle of tangency. Cool. You see what I'm talking about? Yeah. Get the like watermark kind of thing. Yeah. Cool. Okay. Good. All right. So this thing is called a Dandling Sphere, and and also there's like an infinite number of them, right? For every size sphere, every different size sphere will get stuck at like a different point. Okay. Good. Can you hold that? Good. Probably you should like dump it in the trash and then give her tangerine back. All right. We are now going to prove that an ellipse is an ellipse, and we're going to do it via this diagram. And is there anything else I want to say? Oh yeah, one more. Oh, I have one more little small remedial geometry fact, which we need to remind ourselves about. There is a theorem from geometry that says a circle, tangents drawn to a circle from an external point are congruent. So take a circle, take a point outside the circle, and draw the tangent segments from that point to the circle. Please prove to me that these two purple lines I have just drawn, call this circle O, this P, AB. Prove to me that AP equals BP. Class. Yeah, I would highly recommend drawing radii, which is like the key to every circle proof. Okay, because like a circle is the set of all points such that their radii are congruent, so then you just automatically get some congruent radii. That seems like helpful. More facts? Yeah, Jacob would like to remind us that the so-called tangent theorem says that tangents are like perpendicular to the radius drawn to the point of tangency. That's very important. Now what? Yeah, now it's just like easy, right? Now you just connect OP, and then these triangles are probably like congruent, right? Why? I think HL is the only correct response, right? Because they have a blue in common, and they have a red in common, and they have a, otherwise it would be like, SSA or something. So yeah, good. By HL, these triangles are congruent, and therefore AP equals BPS. Okay, good, say good. Okay, and then also this works for the Tangerine back. Thank you. Also, this works for a sphere as well, right? It's basically the exact same proof. If you take points drawn to a sphere, tangents to a sphere from an external point are also congruent, yeah? Okay, good, thank you. All right, good. Without further ado, we shall prove that an ellipse is an ellipse. Can you give everybody one of these? I want one too. All right, and please be nice to me because this is hard. This is really hard to draw. Even though I do it every year, every year I find it difficult. I will try my best. Like what? Okay, good. Good. So first we start with so you're gonna have this picture, and the picture just means that you don't have to be good at drawing because the picture's here for you, but that's also bad because the picture just like appears completed. So we're gonna like make the picture step by step. Follow? Okay, good. And maybe you wanna lift that up and like move it closer to like behind Charles or something. Up to you. All right. So first we have a cone, and the cone.
Too soon.
It's like already dead. The cone is called C, and this point up here is O. And now I am going to pass through, and the cone continues off, but for the ellipse proof I only need like one nape of the cone, so that's like good enough, right? All right, now I'm going to pass through this cone a plane. Sorry. I'm going to pass through this cone a plane, and the plane is called pi. All right, so here comes that's just what this worksheet decided to call it. So, all right, I can do this, right, guys? Sure. Yeah. And give me art suggestions. If I'm doing something like really bad, like no, dude, that's really bad. Okay. Good. So this plane is called pi. All right, and I have the axis is here, right? So this looks like there's going to be an ellipse is going to be formed, right? Because it's at the appropriate angle, you know, just from eyeballing it to make an ellipse. All right. So what is that ellipse going to look like? Well, it's going to be at the intersection going to be at the intersection of the plane and the cone. And let's call this ellipse E. All right, and you can already sort of see what's going on here. Essentially what I'm doing is I'm adopting as my definition of an ellipse the geometric one, which seems to be like the way to go, right? And now taking the geometric, which is the original definition of an ellipse, as like the main one, I am now going to prove that it's equivalent to the old definition of ellipse, which is the one that the sum of the distances to the foci is constant. Okay, and I'm going to do that by showing that this ellipse has that other thing as like a property. So what I need to do is I need to show that this shape has the property that the sum of the distances to the foci is constant. All right, and I don't even know what the foci are, so I'm going to do that too. And this is kind of awesome. Inside this cone, I will now put a sphere. And there are an infinite number of Dandling spheres, as we mentioned, right, of every possible radius. So put like a small one in there, like a little tangerine, right? And now let it get bigger and bigger and bigger and bigger. And as the sphere gets bigger and bigger, staying tangent to the side of the cone, it moves like farther and farther down the cone, yeah? But eventually it will get stuck because there's a plane in the way. Oh. And where is it going to get stuck? Is it going to get stuck at the center of the ellipse? Yeah, because the plane's like tilted, right? Because it's not a circle, it's an ellipse. So since the plane is tilted up, then the expanding Dandling sphere is going to like bump into the ellipse, like kind of like to the right. Follow? Yeah, good. And so that point, I will call innocently F1. So, and now, oh God, this is the hard part.
Oh no.
Don't laugh, you. Something like this. No, that's okay. I knew you were going to laugh. Whether it was good or bad, you would laugh. All right, good. So this is my sphere. I'm going to call this sphere S1. And this is the circle of tangency. This little circle is the, which we will call R1. R1 is the set of points that the cone and the sphere 1 have in common. Everyone following this? It's pretty good. Okay, and F1 is the point of tangency of this sphere and the plane pi. So it's the point where the sphere bumps into the plane pi and can't get any bigger. Is everyone okay? Maybe this is like not that hard. All right, good. And now I'm going to repeat the same thing on the bottom. I'm now going to take a really gigantic Dandling sphere, and I'm going to shrink it and shrink it and shrink it and shrink it and shrink it until it bumps into the plane. But it's going to bump into the plane like kind of on the leftish, right? Because again, the plane is like tilted down. And so I'll call that point F2. There we go. That could be worse. Again, could be worse.
Everything could be worse.
No, that's pretty good. Okay, good. So let this be sphere S2, and let this be R2, the circle of tangency of the of sphere S2 in the cone. Any suggestions, or is that like kind of decent?
You can tell what's going on.
Yeah, okay, good. I'll take that as good. All right, good. So now, well, what do you think about these points F1 and F2?
They're the foci.
Yeah, they're the foci, or I can call them the foci. And so now, in order to complete this proof, what must I prove?
They are the foci.
That they are the foci. Could you be more specific?
F2 and
Every point
F1.
on the ellipse is
Hirsch.
that every point on the ellipse, or the sum of the distances from each focus to that point is constant.
Yeah. Hirsch says, yo, if you take these points of tangency of the Dandling spheres to be the foci, then what we have to prove is that F1x plus F2x is a constant for every for every x on ellipse E. In other words, if I take an arbitrary point somewhere on this ellipse, I'm doing basically a geometry proof now, right? If I take an arbitrary point somewhere on this geometric object, I need to prove that the sum of the distances to the foci is constant. Okay, well, let's do it. Let's take an arbitrary point P. And let's let this point P be just an arbitrary point chosen on the ellipse. Cool? Alright, and now what I'm going to do is I'm going to draw the line or the ray OP. Whoa! I do. My nose was bleeding just this morning. It's like very dry everywhere.
I want to go to the bathroom.
Yeah, you should probably go to the bathroom. You're good.
Take the box with.
That's leadership right there. Yeah, are you gonna be okay? Should we send like a quick helper maybe?
Amanda will take the tissue box with you.
I think he probably seems like they're kind of okay, but just let's confirm. All right, good.
Yeah, I agree.
Or not, I don't know. All right, good. Anyway, finishing this off.
He wiped the door.
Good. OP. So what is OP? OP is a ray that's running, but now since we're connecting P, everyone keep because the picture's not amazingly great, it's just good enough. So P is a point on the ellipse, right? Which means that P is on the intersection of the cone and the plane. So P is a point on the outside of the cone, yeah? Okay, and O is obviously the vertex of the cone. So the line OP is running like along the outside of the cone, so to speak. Okay. Now, I will do something awesome, which is I will find the points of intersection. All this is on the piece of paper, by the way. I will find the points of intersection of this line and the circles of tangency. So let's see, let this point be called Q. And let this point be called T. So what are Q and T? Q is the intersection of line OP and circle of tangency R1, and T is the intersection of line OP and circle of tangency R2. Cool?
Yeah.
Okay. And so now I don't need any of this, so I'll erase that. And now something kind of brilliant happens. Oh, and I also don't need any of this, so I'll erase this too. And now I just have this segment QT. But what happens as this segment QT, as this point P moves around the ellipse? Let the point P just kind of come alive now, and let the segment QT just move around and around the ellipse. What can I say about this? QT is constant, right? QT is constant because what is QT? It's just the, I guess in words, QT is like, it's sort of like the distance between the circles of tangency, right? Yeah. But measured along the outside of the cone. So it's the distance between the circles of tangency. And once you give me a particular cone, and once you give me a particular plane, then there is only one upper Dandling Sphere, which is tangent to the cone and also that plane. And there's only one lower Dandling Sphere, which is tangent to the cone and the plane. And so the circles of tangency are fixed. And so this point P sort of moves up and down along this segment QT, but the segment QT itself stays constant. Okay, well, this is the fun part. If you get the foci into it, well, take this segment PF1, for example. Okay. What can I say about PF1? Yeah.
PF1 is tangent to the sphere. Yo, I get it.
And therefore
QP equals PF1.
Yeah. Okay, this is a little bit hard to see, but he is exactly right, right? PF1 equals PQ, because both of them are tangents to sphere S1. PQ is certainly a tangent to sphere S1 because Q is a point on the sphere, and PQ is going along the cone, and the cone is tangent to the sphere. But PF1 is also tangent to the sphere because the sphere is just sitting right there, right? And since P is on the ellipse, and since F1 is in the plane of the ellipse, then PF1 is all that segment PF1 is on plane pi, follow? And so PF1, so these two are congruent because tangents drawn from an external point are congruent. You guys get it? Okay, and then what other two segments are congruent?
PF2 and PT.
Yeah, if you also connect PF2, then PF2 equals PT. Because again, those are tangents drawn to the sphere from external point P. Point P is not on sphere S2, but PT is tangent to sphere S2 because PT lies along this line OP, and that's hitting point T on the circle of tangency. And PF2 is also tangent to sphere S2, sort of from the top. And so, since this is true, and PF2 equals PT, then we're basically done, right? Because now I take, given this arbitrary point P, if I take the sum of the distances to the foci, well, the sum of the distances to the foci is, just by substitution, PQ plus PT, and PQ plus PT is just QT, which is a constant for any particular cone and plane. Whoa. Is you like excited or kind of slightly impressed, or I don't know, it's pretty amazing, I think. Alright, this is the actual proof that we really are talking about the same object. And these Dandling spheres are used basically to do this proof. There's one more thing I was going to say. Oh yeah, you can kind of see this point P as this point P moves around. You can sort of see like as it gets like kind of up here, like PQ will be shorter, which makes P closer to F1, right? And then when P is farthest from F1 and closest to F2, that's when, like, anyways, this is, we need, like, animation. In, like, 30 years, I'll be able to go, like, and everything will just move, but we're not there yet. I was going to say something else. Oh, yeah, so talk to me about hyperbolas. What happens in a hyperbola?
Oh, yeah, it's the differences.
Wait, before we get to that, are you kind of, like, do you feel suddenly, like, enlightened that what are foci really? All along, foci, which we initially described as like, oh, no, they're just like 2 points, man. They just start with 2 points. No, they really had like an actual geometric significance. They are the points of tangency of the upper and lower Dandling spheres to the intersecting plane. So like that's kind of cool. And what is this constant? You could just think, oh, the constant, I don't know, it's always like the length of the string or whatever, just like the string. No, that constant has again like a deep geometric meaning. It is the distance between the circles of tangency of the Dandling spheres. Alright, and then like a hyperbola, now you're going to have the plane intersecting both parts of the cone. So now you're going to have a Dandling sphere like in one nape of the cone and like a different Dandling sphere in the other nape. Are you guys seeing that? It's kind of like hard to draw. I'm not even going to attempt to do it. And what about a parabola? Now you have only one Dandling sphere because, what is this?
Oh yeah.
Yeah, do you see it? It's on the top, right?